All right, without further ado, and starting on time, the next speaker is Nick Vlassis, who's an assistant professor at Rutgers University, and is going to talk about inverse mechanics problems with multimodal latent space diffusion models. Please.
Thank you for the invitation and for putting this together. It has been a very interesting 2 days. So what I wanted to do today was try to showcase some of the work that we've been doing this last couple of years with diffusion models to solve inverse design problems, and so how versatile they are to work with many different types of data if we work at data structures, if we work in a latent space. So whether you want it or not, you know what a generative AI model is by now. These are AI systems that are tasked to create new data instances that resemble the training data by learning patterns, structures, underlying distributions or properties of distributions to generate similar data that have properties that belong in these distributions. We've been working with a lot of different modalities: images, text, sound, videos. And in mechanics, we've been using them a lot for topology optimization, material and structure design, modeling, constitutive modeling, physics solvers, and reduced order modeling. And when we play around in these latent dimensions, these topics may start intertwining in funny ways. So I will be focusing on diffusion models, but one way or the other, all the generative AI models out there can be considered latent space models. They involve 2 steps, starting from our data manifold, where all our real data exist. The models, be it a variational encoder, a GAN, a diffusion model, are tasked in some way to embed these samples into a latent space. That's where the representations and all our learned properties exist. And the second step would be sampling from a neighborhood in this latent space around somewhere that hopefully our data with specific properties exist, and moving back to the original data manifold. Selecting this neighborhood in the latent space would be what we call in diffusion models conditional generation. Okay? We try to pick a neighborhood which should have the properties that we expect it to see. So what are diffusion models? You've heard about them a lot these last 2 days. These are models that add noise, a Gaussian noise usually, little by little in a sample until the original signal of the sample is completely destroyed. And then they're tasked to remove this noise little by little, again, until they create a coherent sample. They've been shown to surpass the previous state of the art of generative models, specifically GANs, in at least perceptual quality metrics. They're still kind of slow. There is this very passive-aggressive paper saying diffusion models beat GANs on image synthesis tasks. Okay, and why we really like them is because they work exceptionally well in conditional settings. And you will see how we've been conditioning the generation in the latent space with our diffusion models. So conditional settings, it means, for the computer science people, usually means text into images. For us, it will mean many different modalities. Okay, so they've been around since 2015, starting from statistical non-equilibrium thermodynamics. That's where the term diffusion comes from. There have been a lot of variations, but the implementations that we've been using are mostly the 2020 denoising diffusion probabilistic models, or DDPMs for short, and they are improved formulation from 2021. So again, how does the diffusion, how do these models work? We start from a sample x0 that belongs in a data distribution queue. We add small amounts of Gaussian noise over T diffusion steps. Usually that's a big number depending on the problem, around 1,000. The amount of noise that we add is controlled by a variance schedule. Beta, a number between 0 and 1, and we add more and more noise. And theoretically, when we reach an infinite number of steps, the signal should be completely destroyed and have a distribution with a mean 0. But in real life, in practice, this happens around 1,000 time steps. Actually, you will see 1,000 could even be an overkill for our simple mechanics applications. What make these models work is the fact that they're modeled as a Markov chain process, meaning every step in this forward diffusion noising process depends on the previous one, and they can be represented as a product of conditionals in a Markov chain. It has also been shown, actually the paper is kind of old, before diffusion models were a thing, that the inverse process, the inverse of a Markov chain that follows very, very small steps of adding noise can be also be modeled as a Gaussian. But it would be very difficult to predict how we remove the noise starting from random noise all the way to a clean image. So whenever something is very difficult, we do the lazy thing, we train a neural network model. Okay? So we try to learn this inverse this inverse process with a unit. Sometimes some people may use transformers depending on the data you're working with, that is modeled again as a Gaussian. What this model does, it will start from random noise, and step by step, again following this product of conditionals, we'll try to create a clean image. But why do we call them latent space models? Well, it's kind of conceptual. We follow the idea they're called latent space models because we try to look at them as variational autoencoders. In a variational autoencoder, we have the input going through an encoder, a mean, outputting a mean and a variance, sampling this distribution to create a latent representation, and then decoding it to get a reconstruction. In the denoising diffusion models, conceptually, you can say that you have a fixed encoding process, that is the process of adding T amount of noising steps, and what's learned by the unit is the denoising process that we call the decoding process. Why do we do that? Because then we can use the common training objective for all latent variable models, and even flow models and GANs, you can look at them as a variational autoencoder, and we do all of that just to use the common training objective, optimizing a variational lower bound. I wouldn't even dare to explain the math behind it because I'm not a mathematician. I'm an engineer, I say at least. The whole concept here is that if we follow this formulation and through a lot of derivations, you can model, you can actually implement these models with very simple loss functions, training objectives. Specifically, a sequence of KL divergences that measure the distance between consecutive Gaussians. Okay? So what I wanted to do here is to showcase a few of the ways how we've been working in latent spaces to solve inverse design mechanics problems. I'm going to talk about some published work on generation of hyperelastic microstructures, how we expand that to generation of elastoplastic microstructures, some ongoing work on generating structures with target deformations, actually the head start on the mechanical MNIST challenge that accidentally happened, detecting discontinuities with DDPMs, just by looking at the deformed shapes, and something similar that Professor Sun talked about, generating granular assemblies with latent space DDPMs. Again, I wanted to showcase, okay, things are glitching out. I wanted to, good thing it's noise, so it doesn't look half bad. Yeah, so what I wanted to showcase is if you have a funny problem setup, you can, or funny data structures, you can work in latent spaces. Okay? These models are very versatile, and hopefully I'll prove that to you, and not that I'm running a one-trick pony operation. Okay? I first wanted to talk about the paper we published back in 2023, where we reframed the DDPMs to not generate images. We don't care to generate images of cats and dogs, but we do care to generate property distributions. Specifically, we use the EMMA's mechanical MNIST dataset to generate distributions of Young's moduli, where our channels are not colors, but they are distributions of a material property in a specific range. And the generation is not controlled by text, even though we ended up controlling it by text as well later, but by constitutive behaviors or target topology descriptors. So again, the dataset, based on the original computer vision MNIST dataset, we just used the uniaxial extension set from the mechanical MNIST dataset, 60,000 training, 10,000 testing samples. For our inverse problem, we input a hyperelastic energy functional and try to predict an inclusion shape, property distribution. Okay, we train a conditional DDPM model. Our model is tasked to start from random noise and embed target energy functionals or target topologies. Pretty much we tell it what we want the final microstructure to look like. And then hopefully it will generate samples from that union of the different contexts we are embedding. But because we start from random noise, we don't fully trust it all the time unless we have a lot of data. So just to be sure what we generate is good, we may add an extra filtering step. This could be a finite element simulation, or if we're lazy, we run a convolutional neural network surrogate that replaces this finite element simulation. So these are some sampling results. We can very quickly generate 2,000 microstructures. This took a few minutes on a GPU, generate many of them, and then we say, okay, the error range is not the best. Let's rank and filter the ones that we actually want. We could do it with finite elements. We do it with but because we don't want to wait, we do it with a CNN model, okay, to select very quickly 500 microstructures that hit the target very, very well. And here we wanted to push the limits of what we can do to see the expressive capacity of our model and try to create microstructures, okay, glitching out, sure, okay, it doesn't want to play, okay, that for shapes that do not really exist in the dataset. So here we wrote the letters alpha, beta, gamma, and then indeed the microstructure, the DDPM tried to generate structures that have this behavior, even though it wasn't trained on these images. Of course, there is a limit to what the model can actually do. In a couple months ago, we published an extension of this work to start from commands in natural language to design microstructures. We said, maybe you don't care. Maybe you're a practicing engineer and you don't care to actually have to code how you input all of these things to generate your microstructures. Maybe you just want to type a sentence and generate a structure that has the behavior you describe. So we set up a system of 2 agents, a natural language agent and a DDPM similar to before. The natural language agent expects a sentence, then performs named entity recognition, extract important descriptors and feeds them to the DDPM to generate microstructures, and then we select the ones that we actually want to keep. So the sequel to this work was trying to design elastoplastic microstructures. Again, we come up with a synthetic data set where we reframe RGB images into 3 distributions of elastoplastic properties: a Young's modulus, a yield stress, and a hardening modulus. We randomly sample them from the MNIST data set. We overlay them to create a composite microstructure, and then we pull at them we perform uniaxial extension tests with the FEM library Moose. We generate 10,000 of them and collect pairs of von Mises stress curves and topologies. Again, now the inverse problem would be inputting stress, predicting this composite microstructure. Again, we set up a DDPM model that starts from now RGB noise, inputs the stress, and tries to predict a microstructure that has this stress behavior. We also add a surrogate model filter because we don't fully trust what we are generating all the time. Even though, as you can see, there is a general convergence towards the behaviors that we want. So this is the surrogate model. It's just a very simple CNN to replace the kind of costly finite element simulations. So it can make predictions in a fraction of a second to fully replace the need for FEM. These are some generation samples for 3 cases that were not in the training dataset. For each of them, we generate 5 samples, and we can see we have a general convergence towards the stress behaviors that we want them to have. So this is what the convergence should look like. Over 1,000 diffusion steps, we eventually start hitting the targets that we want. These are the CNN predictions. We do it because it's very quick to check how things are going. Okay, so we don't necessarily always want to design structures just based on their constitutive behavior. We may want to design structures that when we deform them a specific way, when we apply boundary conditions a specific way, they get a specific deformed shape. So here, we generate yet another synthetic dataset. We start from the number 7 of the MNIST dataset and perform, okay, it's freaking out, cool. You kind of get the point. We perform a lot of inflation simulations. Okay, think of balloons. Why the number 7? Because it kind of looks like a robotic finger, a soft robot finger, right? We fix the number. We fix the domain from the bottom, apply a uniform pressure profile that increases over time, and then we create a data set of deformed shapes and initial images. The idea here is to try to input the deformed shape, descriptors of the deformed shape, and design candidate structures that maybe we can 3D print. Okay. We generate 7,000 simulations with a Neo-Hookean material, but we can do a lot of augmentation that respects boundary conditions like flipping, shifting the images left and right. So what I wanted to point out here is that this thing works because it is based on a fixed processing pipeline. Okay. This is something we discovered as we were playing around how we're going to parameterize the model. How we actually arrive to the simulation has 10 steps. We take the original image, we call it the structure basis, binarize it, fill in some gaps, expand the boundaries, combine the two together, shift it down so we can hold it. Okay, define subdomains, delete some, apply material and boundary conditions, and run the simulation. So the question is, which one do we input for our DDPM? What we discovered is that the DDPM, if you follow these fixed steps, both in pre-processing and post-processing, you can work with any of these that you like. Specifically, we pick the grayscale images because they are the simplest, smallest, and more efficient to work with. Okay? So implicitly, the DDPM learns all these processing steps. So you can connect these very two abstract images with the actual simulation results. That really looks funny right now. Okay. So how do we describe the deformed shapes? We come up with some simple descriptors, a height, a width, a bounding box, or an aspect ratio, the area of the convex hull, or we call it the medial axis, pretty much the midpoints of the deformed shape. That gives us an idea which way the structure is going to go. And these are going to be the basis for our DDPM input. Okay. We can input any combination of these descriptors, start from random noise, generate a grayscale image, but then we have a fixed processing pipeline that is implicitly learned by the DDPM. The DDPM never sees it, but it knows how to connect this image to the generated, developed structure. So these are some results for target heights that were not seen in the training set, target widths, target aspect ratios, target convex hull areas, and target medial axis. Okay. Of course, we start from random noise, so sometimes we may not get super accurate results, but we can always double check with a finite element simulation. Okay. The idea is to quickly come up with a candidate, or many of them, and select the one that's the most feasible, the easiest to 3D print or whatnot. Okay. So finally, well, not finally, I have two. Two more. Accidentally, we got a head start in that MNIST challenge you were talking about yesterday. We said, what else haven't we tried to pair together? Well, previously we looked at constitutive behaviors to figure out what's happening inside the material, but that's not something you always have. What we easily have are images of the deformed shape. Maybe we can, something you would do with digital image correlation, maybe ideally, hopefully something you can do with your phone, okay, in the future. So we said, let's set up an inverse problem that we input a deformed shape and predict the stiff inclusion and maybe distribution of the Young's modulus. We describe the deformed shape as a 2D field of deformations. We describe the stiff inclusion as a point cloud weighted by, every point weighted by the Young's modulus. And why do we do a point cloud? Because the aspiration here is eventually to work with non-regular shaped domains, okay? Not always working with squares. So the idea is eventually we will look at funny domains and try to predict with a point cloud what's happening inside. Because there are not that many very well-established DDPM models that work with these types of data structures, we said, let's operate in a latent space for both. So that's what we do. We set up autoencoders to compress our deformed shapes into 4x4 codes. We can train them offline or during the DDPM training, and we can see the reconstruction capacity is very good. We can do the same for the point clouds. This is more important because there are not that many point cloud autoencoders. Specifically, we use a very established one, the folding net, because it comes with a chamfer distance function, that's for point clouds, and it works very well with different number of points. Here we see the reconstruction capacity. Okay, we start losing some details, as you do when you're compressing information, but here we want for a qualitative understanding of where things are. But now that it's a competition, maybe we're going to go back and fix it. Okay. So we work with two latent spaces now. The latent space of the deformed shape and the latent space of the point cloud. The DDPM works, adds noise to the point cloud embedding, and the UNet, knowing what's happening through the deformed shape code, tries to remove the noise and eventually converts into a point cloud inclusion. Okay? So these are some results. Here we realize that 1,000 steps may have been an overkill. Usually the last 20 steps is where all the action happens, and we start converging into the target inclusions. Okay? And the idea here is how we want to, every generation is one probable inclusion. How do we pick the most probable of them all? We look at two approaches. One would be generate a lot of codes, take the average of them, decode them, and get the most probable point cloud. The other would be to generate a lot of codes, decode each and every one of them, overlay them, do some clustering, and then select what the algorithm thinks is the most probable. Even though it's not a definitive answer, we think the averaging method worked the best. So, okay, why we do all of that? How much deformation is enough deformation to understand what's happening? We did another training experiment where we added all the deformation steps, I think it's 12 of them, in the DDPM, and we saw what the DDPM starts predicting the more and more we pull the material. In the beginning, in the deformed state, it cannot really tell it's the number 5 because it just looks at a square. It could be different shape inclusions and it wouldn't know. The more and more we pull at it, we start converging to the number 5. We can see that qualitatively, and we could also see that from a general downwards trend in the chamfer distance. The more we pull at it, the lower the error. Okay? Again, it's noisy, so it may go a bit up and down. Cool. Very quickly, because Professor San already kind of talked about the next version of that. Yes. We also work with latent spaces. In latent spaces to design granular 3D sun grains. Okay, a big thing in granular mechanics is that we never have enough sun grain shapes to do a quantitative analysis of how these affect the overall behavior of granular ensemble. So we were given some F50 sun grain data set. about 1,500 of them, segmented and very nicely reconstructed. And the idea is turn them into point clouds, encode them with a point cloud autoencoder in a latent space, add noise, remove the noise with a unit, decode it, and eventually, hopefully, converge into a realistic sun-grained point cloud. Okay? These are some generation results. You don't see what's happening in the latent space. You just see the decoded part, starting from random noise, converged to the point cloud that we can then mesh and run our simulations in. Okay? These are some database and generated sun grains. If you squint, you can be fooled that they look realistic. Okay, there is a bit of a smoothing effect from the autoencoder. But what we see is that we learn a very good underlying size and property distribution. Okay? We started from 1,500, generate 50,000, and less than 0.2% of them fall under the same size and shape distributions. Okay? And then we can generate as many as we want and generate our granular assemblies to run our simulations on. Okay. So again, hopefully I've proven to you that if you have a funny inverse problem that you don't know how to work with these data structures, just work in a latent space. Find a good autoencoder, create the latent space, and then do your classical image diffusion models in this space. Okay. I would like, quickly some of the literature I talked about, and I would like to thank you for your attention. Thanks.
Right. Thank you very much for the talk, and we open the floor for questions.
Okay, great. Thanks, that was a great talk. I have a really naive question. How do you do the conditioning? Are you doing something like classifier-free guidance, or you're doing it as a post-processing?
It is classifier-free guidance, okay? But pretty much it's very simple. So the unit model expects, let me go back to one of the conditional ones. The unit model expects, further back, expects an embedding of time. And the way we do the conditioning, we also literally add up another embedding. Yeah, so you see that's the time embedding that tells you what time step in the diffusion you are. And then we just add up the context embedding that comes from another embedding architecture, a very, very small neural network that you input a descriptor, turn it into a vector, add it up to the time embedding, feed it to the unit architecture. Okay. And then it is classifier-free because we do the trick that you drop the context like by 10%, the thing that they do it. It is learning. The unit is an estimator of two things. Either it can generate images that look realistic by, that's the 10% that you're dropping the context, or 90% paired with the context, yeah.
Okay, thanks, Nicholas.
All right, we have time for one more question. There we go. Steve.
Hey, Nick, thank you for the wonderful talk. So I was wondering, for this generated structure, have you considered the case where you're not generating one stable structure but multiple one? It's possible, because a lot of cases where you want to deploy a structure, you start with a very small structure, and then there are multiple configurations. Do you think how you can achieving that?
Yeah, so here we do the kind of naive way. So I had an idea for your, maybe I don't know how much we should keep bouncing back and forth. Everyone should do their own thing. Okay. But for example, in your sun grain assemble thing, right? You want to fit your sun grains in your bounding box, and sometimes they may not fit very well. Well, what if the naive way to do it, the brute force, is keep generating again and again until you eventually generate one. It's very cheap to generate, until you generate a sun grain that fits exactly what you want it to do. But you could do it, you can push the AI to do it with a bit of conditioning or some other tricks. I'm sure put in a loss function or something, yeah.
Let's say you have a sequence of different boundary conditions. You want to create one microstructure and then another one. Do you think it's possible?
Oh, okay. Yeah. I see. So find a microstructure that follows a lot of boundary conditions at the same time, pretty much?
Instead of having one target microstructure, you have multiple Like a transformer.
I see.
Toy transformer.
I see.
Not the neural network.
Yeah, I haven't thought about that. I don't know if that's a very funny way you can do the conditioning. Maybe a path-dependent conditioning, or maybe have another classifier pushing your, while you generate, pushing your structures to during the generation. But I'm not sure. I'm not sure about that. Yeah. Cool.
All right. Let's thank Nick once again for a wonderful talk.